All right, now that we have some idea of torque, we can apply these things to equilibrium problems. This is going to be the important part. A very important part of engineering deals with building structures that neither move nor rotate. So we have to understand the physics behind this. Again, these are problems that are going to extend what we know about Newton's laws. It deals with objects, again, that are not moving or rotating. For something to be in equilibrium, it can't be moving and it can't be rotating. Physics-wise, this is going to reduce to the Newton's second law equation being set to 0, as well as a condition on torque. The first condition we have, sum of the forces have to add up to 0. If we have 3 dimensions, sum of the forces in all the dimensions have to add up to 0. This we've done before. That should be no problem for you. There's another condition, though. If my object is not rotating, that means the sum of all the torques about any fixed point have to be 0. Mathematically, it's given by condition 2. The sum of the torques about any point have to add up to 0. You're familiar with condition 1. Condition 2 is the new twist that we're going to have to learn. Best way to see this is through an example. You should be familiar with a teeter-totter. You guys played on teeter-totters when you were growing up, so you know how all the physics works. Consider a teeter-totter that's 6 meters long. Pivot in the center just like you've seen before. We'll assume the teeter-totter has a mass of 50 kilograms, and there's a 45 kilogram child at the far left end. I want to put a 50 kilogram child sitting on the right side in order to balance it, but where should I put them? So here's my teeter-totter. 50 kilograms, they're my 2 people. I've got their 45 and 55 kilograms, and I've got all the forces identified. Notice I've got a 450 Newton force down, a 500 Newton force down, a 550 Newton force down, and then a normal force up. All of that should be familiar with you. I've added some dimensions so we know where things are. I have one arrow representing the length of the teeter-totter, which is 6 meters. My pivot's in the center, so I have an arrow that's 3 meters long showing where the normal and the weight act. And then I have another arrow, x meters, an unknown quantity, figuring out where my other person has to sit. We'll proceed like I've done before. I drew a picture, I ID'd the forces, I'll define a coordinate system, and I'll eventually write N2 for all the directions appropriate. Here's my coordinate. I can use the picture on the last slide and write out my N2 equation. I don't have to worry about the x direction. There's no forces acting there. Here's my y equation. Fn minus 500 minus 450 minus 550 equals 0. It's an interesting equation. It tells us how strong the normal force or the pivot has to be, but it doesn't tell us anything about where the 55 kilogram person has to sit. So we need more. Now, let's pick a point to calculate the torques about. It doesn't matter where we pick the point. With a little bit of thought and a little bit of knowledge, you can pick a good point and make the math easier. But you'll always get the right answer no matter what you do. I'm going to pick the point to be the pivot point of the teeter-totter. Now let's think about what definition of torque is. It's a force times a distance. Notice that both the weight of the teeter-totter and the normal force act at the point we picked. As I've mentioned before, we'll always assume that the weight of an object will always act in its geometric center. If I pick this point, then since W and Fn both act there, the torque exerted by both of these are 0 because they're both located at the pivot point. That's the type of choice you need to make. So now what I'll do is I'll start at one end of the teeter-totter and move across it to the other end, finding all the forces that act and calculate all the torques that act, in this case the pivot point. First force is the 450 or the 45 kilogram person sitting on the left end. That force is 450 newtons and is 3 meters from the pivot. That means the torque is going to be 450 times 3 or 1350 newton meters. What is the direction or sense of rotation? That can be a little bit tricky. Think of the teeter-totter as a giant propeller, and it's going to rotate about the pivot point. If no other forces act on it other than the 450 newton weight on the end, which way would the propeller want to rotate? In this case, it would want to rotate in a counterclockwise direction. I'd be pushing down on that end, See how it might circulate around. It looks like it would go backwards from a clock sense, so that's counterclockwise. I'll call counterclockwise my positive sense. I typically call the first rotation I come across to be positive. The next two forces I come across as I move across the teeter-totter are W and Fn, but both of these act at the pivot, so the R is 0. That means both of these torques are going to be 0. That's why I picked that point. I eliminated 2 of the 4 forces in the problem. Finally, I come across the last force. That's the 550 Newton force, which is the weight of the person on the right side. That person is located a distance x from the pivot point. So its torque is 550 newtons times x meters, or 550x. That's going to be an algebraic expression. That's okay. Its sense of rotation about the pivot point would be clockwise. Think of the giant propeller again, so it would want to make the teeter-totter spin in a clockwise direction. In my coordinate system, that's negative, so my torque equation is going to be 1350 Newton meters minus 550x equals 0. I can use this equation to determine where x should be. Solving this gives 2.45 meters. This should make sense when you used to play on a teeter-totter. You place the bigger kid near the pivot so the smaller kid could balance the teeter-totter by sitting further away. It takes a little bit of practice. It takes a little bit of skill in determining the direction of the torque. We will only use clockwise and counterclockwise as our directions. That should make sense from things that rotate. I do things a little bit differently than most books. The first torque I come across gets defined direction-wise as positive. Then I determine the other directions with respect to my first one. What if I picked a different point? What if I picked a different place to find the torque about? All that happens is the math becomes a little bit more complicated. I have to get the same answer. So let's try it. We're going to do the same problem, but now we're going to find the torques about the left end. So here's my teeter-totter picture again. Everything's the same as before. But now, my y equation will be the same, but now my torque equation will change. First force I come across is the 450 Newton force, but it's located at the pivot point, so this torque is going to be 0 Newton meters. Next I come across both Fn and W. Both are located 3 meters from the point. The normal force wants to rotate it in a counterclockwise way, so counterclockwise will be positive. The weight of the board rotates it in a clockwise way, so it will be negative. Mathematically, I get Fn times 3 minus 500 times 3. This is an algebraic expression, so there's not a whole lot I can do with that one. Finally, the last force is the 550 Newton force. It acts a distance 3 plus x away from the pivot point at the left end. So I get for that torque 550 times the quantity 3 plus x. That simplifies to 1650 plus 550x. This force causes the board to rotate clockwise, so it's also going to be negative. Adding all these together and setting to 0, I get 3 times Fn minus 1500 minus 1650 minus 550x equals 0. I have two equations with two unknowns. My y equation allows me to solve for the normal force. My torque equation will allow me to solve for x. If I solve the first equation, I get the normal force to be 1500 newtons. I substitute this into the second equation, and it becomes 1500 times 3 minus 1500 minus 1650 minus 550x. Simplifying gives 550x equals 1350, or x equals 2.54. That's exactly what I got before. Here's one more example. This time I won't use any numbers. I want you to think about like a diving board, like the ones you see at a pool. Here's my diving board. I've got two supports on the left side, and I've got a person standing on the right side. Here are all the forces: a left support, a right support, the weight of the board, and the weight of the person. I've identified the forces and drew them in, but here's the rub. One of these forces happens to be in the wrong direction. How do I know? I can use the torque equation to figure this out. First, let's find the torques about the left end. In this case, FL exerts zero torque since it's at the point of rotation. FR causes a counterclockwise rotation, while both W board and W person cause a clockwise rotation. Since I have one positive and two negative numbers, I could in principle add those together and would add up to zero, so this should be okay. But now how about the right support? Let's find the torque about the right support. Now F sub R exerts zero torque as it's at the point of rotation. F sub L causes a clockwise rotation, but so do both W board and W person. In order to not rotate, one of these forces must be in the opposite direction. Now I know that the weight of the board and the weight of the person are both down, so the only one that could be wrong is F sub L. F sub L has to be in the wrong direction. It has to be directed down. Diving boards are always bolted down at the end. Hopefully this little lecture will make sense with equilibrium and torques. This is about what I would expect you to be able to do on exams and tests.